In this example, we are going to calculate the maximum power that can be transferred to the load resistor RL. The maximum power transfer theorem tells us that for a simple circuit like this, if R2 that is equal to R1, R2 will have a maximum power. So we know that to find the value of RL, we need to find the resistor of this whole network, R1. So if we look at the first half of the circuit, that becomes a Thevenin equivalent circuit with a voltage source with one resistor in series with that. So we need to first find a Thevenin equivalence for this circuit. To find a Thevenin equivalent circuit, we need to go through the whole process, because this problem contains both the independent and the dependent power sources. We need to use the general method. So step 1, we're going to find an open circuit voltage VOC. So we open this RL, find an open circuit voltage. Let's draw the circuit. When you see a circuit like this and you try to find a voltage in the circuit, you have many choices that you can do. So we're going to use the nodal analysis to solve for VOC. First, we're going to select a reference node. Let's select reference node to be here. Label all the nodal voltages. So this node have a nodal voltage of 100 volts, and this node have a nodal voltage, say, we don't know, give it a name V1. Then we can write a nodal equation by looking for the current leaving this node adds up to 0. So we have a V1 minus 100 divided by this resistance, that is a 4 ohm, plus the current in that branch, that is a V1 minus 20 divided by this 4 ohm, plus we know this node voltage have a voltage of 100, and over here this is a 4Vx, so we know the nodal voltage here. So the nodal voltage here, that is equal to 100 plus 4Vx. So we have a V1 minus 100 plus 4Vx divided by the resistance, which is a 4 plus 4, that is equal to 0. So now we completed our KCL equation at a node V1. The second equation is about the control variable Vx. From this branch over here, we know that a Vx is equal to V1 minus 20. Then we can solve the equation to find a V1 and Vx. So we find a Vx is equal to 240 volts, and a V1 that is equal to 260 volts. Then we can find a VOC that is equal to, let's do it following this branch over here to find a VOC. So VOC that is equal to V1 plus the current times 4. The current can be calculated by using the voltage 100 plus 4Vx minus V1 divided by 8 ohms, then times 4 ohms. That will give us 660 volts. So step 2, we're going to find a short circuit current, ISC. Let's draw the circuit. This circuit is something similar to the one that we deal with in chapter 3. So you can either use nodal analysis or loop analysis to find a short circuit current ISC. And we also know that if you use loop analysis, and you will have 3 loop currents or mesh currents, and you have 3 equations on that, and on top of that you will have another equation for the control variable. So in total you have 4 equations to solve. And if you use nodal analysis, so in total you will have 2 equations. So actually nodal analysis for this problem is simpler compared to loop analysis. Since we already reviewed the nodal analysis from the first part in step 1, and we also did a nodal analysis from the class. So in this video, and we are going to use loop analysis to solve this problem. So to use loop analysis, we first need to define the mesh currents. Let's define the mesh currents like what I have here. I1, this is my current I2, and this will be my mesh current I3. I have my 3 mesh current. So let's write the loop equation. The first equation is about the first loop. Let's count the voltage drop. The voltage drop on this 4 ohm resistor, that is I1 minus I3 times 4. And on this 4K resistor, that is I1 minus I2 times 4 kilo ohm. So let's wrap it together so it will become 4 plus 4, that is 8 I1 minus 4 shared between 1 and 2, so that is 4 times I2. Then the 4 kilo ohm shared between the mesh 1 and 3. So minus 4 times I3. The voltage drop on these two power sources are 20 volts minus 100. That is equal to 0. So the equation for the second mesh, we have 4, that is 8 I2 minus 4 I1 minus 4 I3 minus 20 volts, that is equal to 0. And the equation for mesh 3, we have 12 I3 minus 4 I1 minus 4 I2 minus 4 Vx, that is equal to 0. The last equation is about the control variable. In this case, that is the Vx. So Vx, that is equal to, we can find Vx by using Ohm's law, which is 4 times the current going through that, which is I1 minus I2. Then we can solve the equation to find a ISC that is the same as the current I2, that is a 55 amp. So step 3 is to find a Thevenin equivalent of the circuit. So Thevenin equivalent of the circuit become one voltage source have a value of VTH with a resistor RTH in series with that. And we also know that VTH that is equal to VOC. We found that before. That is 660 volts. And RTH can be found by using VOC over ISC, which is 12 ohm. The last step is to use the maximum power transfer theorem. We know that for the circuit like this, it requires RL that is equal to RTH that is equal to 12 ohm, such that it will receive maximum power that is equal to V squared over R, V that is half VTH over RL. That gives us 9,075 watts.